presentation on the T kernel driver that I'm currently trying to upstream. First, some terminology. A T is a trusted execution environment, which is a trusted OS running in some secure environment. There's a number of T implementations, but each of them has their own out-of-tree kernel driver. Secure world that we are going to talk about in this presentation is based on trust zone, but it could be other technologies also, like virtualization or a separate secure co-processor. By the way, if you have any questions, please interrupt during the presentation and I will try to answer. Oh. Yeah, I will do that. The components in this T software stack is we have user space, and we have a kernel driver, and we have a trusted OS. In the picture that you see here is typically a V7 system, but from normal world point of view, it's more or less the same if it's a V7 or V8. In user space, we have the T client library and a T supplicant. I will go into the details of this a bit later. And then the thing in the red circle is the kernel driver, which consists of, well, the T subsystem and a driver. And then in secure world, we have the T itself. So in user space, we have the T client library, which we build on top of the user space API that is provided by the kernel. For opt-T, we are using a T client API 1.0 as specified by a global platform. But for other Ts, it would be possible to use another API if that would be needed. I mean, it doesn't necessarily have to be a global platform. Another component in user space is the T supplicant, which is a helper daemon for the trusted OS. Different Ts has different daemons because they have different needs, and well, it's not standardized either. This daemon can typically provide file system access or access to some shared resources. The user space API provided by the T driver, or actually the T subsystem, is the component that exposes it. It's modeled after the global platform T client API quite closely, but here we can see how the different functions are mapped. So we have, when we open the device, it's like initialize context in global platform speak. And when we close that file descriptor, it's like a finalize context. And then we have open session, invoke command, close session, and so on. Shared memory is mapped as usual by mmap. And it corresponds to allocate shared memory in global platform speak. When we come to the kernel driver, the T subsystem, it provides basically two sets of APIs. We have the user space API that we have just discussed, and then we have an API towards the T driver that handles registration of the driver and the callbacks that the driver has to provide. And then also it manages shared memory between user space, kernel, and trusted OS to avoid having all the different drivers doing their own implementation. And then we have the driver itself. This one is specific per trusted OS, since it handles the communication with secure world, how requests and responses are passed and received, what parts are, how we interact with the TIS applicant, what tasks can be done. Our T, for instance, need help with some synchronization and stuff, but other may have other needs. And it could be, file system access, as we had mentioned before, and sleeping. So shared memory is a must if we have bandwidth-intense applications, and like the DRM use case that was described just before, that's typically bandwidth-intense. The current model we have implemented is more or less what OPTI requires. It's a reserved region of physical contiguous memory. But as we add support for other Ts, we could change this in different ways. It's not set in stone. So a shared memory chunk is represented as a T-SHM inside the T subsystem and drivers, and known as a struct DMA buff to the rest of the kernel, and actually user space also. This SHM struct has a couple of different fields, like the TDEV, which is used for reference counting on the driver. We have the virtual address inside the kernel that can be used, and then the physical address, which is often needed when communicating with the secure world, and so on. When user space is accessing shared memory, it do that by mapping a file descriptor that it basically is connected to this T-SHM. Secure world has another representation of shared memory. It has it's based on physical address and length instead. Reason for that is, well, virtual addresses mean something different in secure world, especially in V8 system. It's hard to connect to what normal world consider what a virtual address is in normal world. So our OPTI driver is implemented as two devices. We have one device that is what the client connects to, and then we have another device which the TIS applicant connects to. It's the division is because it could be that this applicant would need to run as a more privileged process compared to ordinary clients, and also if this supplicant is misbehaving, it could more or less lock secure world, so we can't do much more if it refuses to serve files or whatever we need. A device is described by a struct tdesk, which contains a name and the ops, which are these callback functions mentioned before. It's in the flags field that determines whether it's an ordinary client device or a supplicant device. The Opti driver uses an Opti message protocol as secure world interface. It basically tells the different SMC IDs, what they mean, and what kind of parameters are passed together with that specific SMC ID. The secure world is entered from the client task that does whatever request it is, so it will continue run in the context. If we look at what the kernel sees, it's the time consumed by secure world will be put on the calling task, so to speak. And then we have the remote procedure calls to the supplicant. Since the supplicant runs as a different task, we have some rendezvous with the mutexes and the completions. And also we have temporary shared memory with the supplicant process. Oops. And yeah, an issue with the shared memory between normal and secure world is that you have to agree on the attributes for caching, otherwise we will get coherency issues. On ARM systems, we say that it should be normal cached memory, write back, shareable for SMP systems, and not shareable for UP systems. And Mark?
Is that specific to Opti or Ts generally? Because you mentioned that a T could be a separate coprocessor.
This is specific for Opti in a trust zone solution. I guess it's quite hard to, I mean, if we would be talking about a secure coprocessor, it depends on the hardware, what kind of attributes we can use. I mean, we want to be as efficient as possible, so if we can use the level 1 cache, for instance, it's good.
Sure, but this is specific to Opti rather than
It's very specific to Opti, yeah. And also here we have a kind of a problem. What is an SMP system and what is a uniprocessor system? And well, the definition is deferred to what Linux thinks is an SMP and what Linux thinks is a uniprocessor system. Because, yeah, for practical reasons. Otherwise, yeah, it would be more trouble than it would be worth, because we would still need to interrupt with Linux. So that's the way I've decided to do it. Yes, I mean, we have this SMP function that you can call to tell whether it's Linux thinks it's a uniprocessor or an SMP, and the memory attributes for the translation tables in that Linux uses is based on what this function returns. So that's why we need to yeah, follow that. So basically, the driver will tell Opti that we are a uniprocessor system, so please use that mapping for shared memory. Yep. So if we add a new driver, what do we need to think of? Yeah, we need to consider RPC. Do we extend the current T-supplicant or do we create a new one? Shared memory. Can we live with the current model or do we need to extend it? And how are IRQ handled? Is it like in Opti, where if we get an IRQ, we just forward it to, we switch back to normal world and let normal world handle it, or is it done in some different way? That's things you need to consider. So the status of this driver is, the latest patch is D7, which I sent out, well, I think it's almost a month ago now. The general interest is quite low. I've gotten not too many comments, especially not on this V5 either. Not totally unexpected, since it's a narrow field. But I wouldn't mind some help with reviewing this driver, especially the internal parts of the generic T subsystem, because that's basically, if you start there, it will be easier to follow what goes on in the rest of the driver. So, any other questions? Yuki.
So going back a bit, I'm a bit concerned is that the APIs are currently designed to only handle contiguous memory. From experience in trying to do this before, it's very difficult to try and transfer stuff to go from contiguous memory to non-contiguous memory in terms of things. Is it possible to adjust it just from the start, even if what you have right now only accepts contiguous memory, being able to change things such as perhaps using a SG table instead of the physical address everywhere, and being able to support things off the bat rather than trying to adjust it later when someone comes in there and then having to rewrite everything?
I'm sorry, I couldn't really follow. Could you speak a bit slower?
Sorry. Okay, so I noticed when you were describing the APIs that a lot of places you just assumed physically contiguous memory, the physical address. I understand that's what you have now, but from experience, I think trying to convert from physically contiguous to non-contiguous later in terms of trying to implement the scatter-gather list turns out to be pretty difficult in terms of validating the client and everything in general. Is it possible to just right off the bat support the scatter-gather lists or something like that instead of trying to do that later?
You mean you would rather see that we try to do that directly now instead of waiting with that?
Yes.
I guess it would be possible. It will obviously make stuff even more complex in the first set, but yeah. And also it depends a bit on the implementation we have in Opti. We more or less require physically contiguous memory, but at some point we will of course need to drop that also.
Do we really need anything other than contiguous memory, though? Is this shared memory region just for a communication channel, and then you're able to pass data elsewhere that's not contiguous to the trusted X use environment?
Just from past experience, yes, people cannot exactly why they would want to use the secure environment to be able to pass things that aren't just pure shared memory. A good example is that if you have something that may be used that requires an SMMU to use, for example, then you can take advantage of the discontiguous memory there.
Right, but if this shared memory region is just for the communication between the secure and non-secure world, the pointers could be passed elsewhere. They don't need to be in this shared allocated region. Like the trusted X use environment can access any memory.
It can access any memory, but when we talk about user space under Linux, then it has to, it will be fragmented physical memory, so we need to have this scatter-gather list or something to tell secure world how the memory is, how it's mapped, basically.
So one example would be decrypting media. So you have a DRMTA on top of Opti, in that the RMTA needs to decrypt the encrypted content somewhere, and that somewhere, or it has to get the content from somewhere. So this is a shared memory, and then it has to decrypt it somewhere else.
So how does global platform solve this today then? There's a global platform solution already that I assume works.
Sorry, I can't hear.
I assume there's a global platform solution that already works today that handles this situation?
Not with the regard. Well, you have APIs to kind of register a shared memory region in user space. But yeah, then you need to take care of that in some way. But of course, that's a theoretical way of dealing with it, at least. I mean, if you register some shared memory in user space, you will probably need to lock it into memory so it doesn't really get paged out or something, because yeah, it will be a problem.
In terms of reviewing this driver, is there are you submitting a test app that goes along with it into the kernel and a reference opti or something that we can launch to stress it out?
Test applications, you mean?
Yeah, a user space test app. Are you going to submit something like that into the kernel?
Yeah, we have a test application that goes together with opti, which, well, anyone can use, basically.
In terms of the user space ABI, from your example where you showed opening the FD to the T, you had dev/tx. So I assume that you can have multiple TEs.
Or here, yeah.
Given that, how is that intended to operate in user space with your, I can't remember the name for it, but the application which ran in user space to manage access to it? If you've got multiple Ts, and you need a T-specific supplicant, how do those supplicants get associated with the correct Ts, and how do they interoperate? Is there any discovery mechanism other than TN?
There's some, I mean, how it looks like today is that the T-supplicant opens the device and checks that it's the kind of T that
okay, so if I'm shipping a generic file system, say I'm Debian or something, I want to be able to use some feature of the T because, hey, we should be able to do that. That's what all this stuff is all about, interoperability. If I'm shipping, say, 50 different T supplicants that are each going to have to be launched and open each of these FDs to figure out if or not they can run, that seems a bit bizarre. Is there no way we can, say, expose something like a UUID or GUID to user space where we can go and determine the correct supplicant to fire off in user space via UDEV or something like that?
Put the information used to enumerate into SysBus.
Yep.
If you think the trick would be just put in SysBus instead of outsource software.
Yeah, for those listening on the microphone and the recording, just Mark can repeat it. We could, if there's some information they're going to use to detect it, can we not expose that in SysFS or via UDEV or is there a standard mechanism by which they identify the T?
Yeah, the mechanism is an ISCTL to get some UUID.
Sorry, I mean at the. Okay, so there's an IOCTL. What information does that provide? Is that something that the kernel could query in advance?
Yes.
Okay. So could we do that?
Sorry?
So could we do that from the bat?
Yeah, that could be done while the driver is initializing. Actually, I think it's done anyway when it's initializing to check that it's really the expected T that it's communicating with.
Okay.
Because, I mean, device 3 defines which driver or which T is there, but just in case, we also probe the T to see that it's the correct version. Of course, in some circumstances, it will probably crash the system or do some unspecific, since if you do an SMC to another T, it could mean something completely different. But
okay, so there's no standardized SMC across all TEs?
Oh, well, we have the SMC calling convention, so provided that the T follows the SMC calling convention, then it will not crash, of course, since we start with, well, doing some of the standard function calls.
Okay. Do we mandate SMC calling convention then?
This is driver specific. I mean, the T subsystem itself doesn't care about SMC. It's only the driver that cares about that. So depending on how the driver is implemented, it could be whatever.
Okay.
I think it could be good to also, emphasize that now we're talking about OpT, but this kind of effort is something we are trying to do now to fill in the gap. We see, there's been a lack of T driver in the kernel. We have seen kernel or T drivers out of tree in different places on the net, but nothing in the kernel yet. So, as Jens said, it's split up in two parts. We have one generic part, and then you have one lower part, which actually talks to the unique.
Okay, but that's fine. It just seems that the generic pod is not providing things that should be relatively common. Even if the API is not common for each T, it should be possible to hand that information over to the generic pod.
Right. That's good feedback. But just so people are aware of it, this is not only for OpT. This is something that should work for our Ts also.
Another question.
My question is about how you manage the shared memory between the secure world and unsecure world. So I'm assuming that when the system gets brought up, you set this piece of contiguous memory.
Yeah, currently it's OpT owns a specific area of DDR, which is non-secure, but it's reserved for secure world anyway. And it tells the driver, here's that memory, use that as shared memory. And then we have a generic memory allocator in the driver that manages what's free and what's not free.
You just answered my question.
Okay, great. Oh.
My question is about the cacheability of the shared memory. If we share a very secure memory inside a shared memory with a cacheability, is there any kind of a possibility to be leaked off some other tasks that can be used inside the same core with the same view of the cache memory?
Sorry, I didn't really get that question.
My question is, if we set a shared memory as a cacheable, and some other tasks can get the cache memory altogether, and then is there any kind of a possibility to be leakage of the data of the shared memory through the cacheable characteristic itself? Did you get it?
Sorry, I don't really understand the question.
Yeah, I will go to you probably.
Yeah.
When accepted, do you have plans to backport it to LSK 4.1?
Sorry, could you repeat?
When your driver will be accepted, do you have plans in Linaro to backport it to LSK 4.1?
I think yes. I mean, that depends if someone requires it, but it's quite easy to backport, I would say. There's not that many dependencies to anything else. So, I mean, we have been running more or less, not this particular driver, but it's almost the same, and we have been running since, 2.6 something way back, and we started 3.4, I think, in the beginning of 2014. So.
Okay, thank you.
Another question?
The functionality that you've implemented in the secure world, I believe one of it is Opt driver. What kind of code review or code validation or implementation validation have you gone through to make sure that that code is not susceptible to some I don't know, like buffer overflow attacks or some other type of attacks that you have an attacker poking around?
You mean in this driver I'm talking about here? Nothing specific. I mean, I've just written the code. So I guess.
Are there any plans?
Sorry?
Are there any plans to do a little bit more of the code validation?
Yeah.
We have no strict plans, but we have. This is one thing we have been asking for, if we could get some kind of help of getting some kind of audit of the entire solution and not only the driver itself. I mean, even user space and secure world monitor and so on. But it's nothing that we have done so far.
One efficient way is to do fuzz testing against it.
So I have two questions. First, I just want to get some clarification to see if my understanding is correct or not. My understanding is that OPT driver you developed that sit in the middle so that you would expect people to write low-level drivers to talk to different T, like some of them would be trust zone, some of them would be secure processor, or some of them might be some other implementations. Is that correct? Okay. So in terms of those low-level drivers, have you already developed some of them? For example, like trusted ARM, trusted firmware, that's open implementation already. Do you have that developed already? I suppose you do, and just want to get a confirmation that you do have the entire stack developed to verify the solution.
Yeah, I mean, I'm not sure I understand the question, but I mean, we have a complete stack, yes. And we have a driver for a trust zone based opt. We don't have the driver for any other kind of opts.
Right, but you design it in a way that is open, that people could develop.
It's
right?
designed in a way to make it possible to use
Okay.
other techniques also.
Okay, good. So another question is, I'm not familiar with that T-supplicant concept. Could you elaborate a little bit more? Is that a user space daemon?
Yes, it's a user space daemon. Let's see if we can find something.
Right.
Yeah, we have it here. And it's in the opt case, we use it for reading up trusted applications from file system, since that's where we store them. And it's also used for storage, secure storage for the TAs. They can store encrypted files and stuff inside the ordinary file system. And then we have what's done in the T-supplicant compared to what's done in the driver. It's a bit of a design decision. For instance, weighting and such things we do in the driver, but file system access we do user space.
Different systems would have different types of shared resources, right? And
sorry?
Different systems would have different types of shared resources. So I would imagine that daemon would be just a prototype code that each system implementer, they would need to update or adapt to the resources their system supports.
Yeah, that's a challenge, and I think that that's also something Mark here touched on with how which supplicant will be used for which secure world, etc. And that's something that we haven't really looked into yet. So currently it's like one T supplicant for one specific OP-T.
Okay.
But that is something that we could improve in the future.
Okay, thank you.
Thank you.
So,
I have one remark about your first comment. So the current OP-T driver is actually used on ARM trust zone and also on a secure coprocessor in ST microelectronics. And we have reviewed this driver, which is the base is the current OP-T driver. And there's no current limitation to have the same, using this driver, to have it target for ARM trust zone or for a secure processor.
thanks.
Sorry, just jumping back to one of the earlier questions, about, you mentioned fuzzing. So if you wanted to look into fuzzing, Dave Jones has the Trinity syscall fuzzer, which you can easily just hand a set of valid FDs to work on, and you could easily provide just the TE FDs and have it just fuzz random syscalls at that and random ioctals, which might help with your testing. It's called Trinity. And one other point that's just come to me with the discussion is the role of the supplicant. For the use cases you mentioned earlier, things like DRM, where you want to get shared buffers out of a user space application, which might require a scatter gather list and so on. Obviously, from the point of view of the user space application, those addresses are going to be virtual, and that's also true of the supplicant. So if any translation is necessary, or if any page pinning is necessary and so on, that's all going to have to happen kernel side. So it seems to me like the supplicant is just going to mediate access to the features rather than being able to provide much of that functionality. What is the role of the supplicant, and why is it not possible for the supplicant work to just be done in the T driver in kernel space?
Well, I think that it's basically file system access that is what's suitable to do in supplicant. Almost everything else is probably better done in the driver.
Could you just elaborate on what file system access?
It's reading files, like trusted applications that we store in the file system, and also secure storage for the different trusted applications. So it's, yeah, persistent storage.
So is that persistent storage provided by the TE, or is this persistent storage on the non-secure side where it's handing stuff to the TE? I'm just a bit fuzzy on that.
Yeah, I mean, it depends a bit on what capability there is in the system, but currently we don't use anything but the ordinary file system to store, for persistent storage for TAs. So that means that if we store some object in a trusted application, it will be stored in the file system, integrity protected and possibly also encrypted. But of course, it's possible for normal world to, well, erase a file or corrupt it or anything.
Okay, thank you.
I may have missed this earlier. So have you tested this against other TEs, or are you looking for the community to test against other TEs that exist?
We have not tested this with any other TE. I mean, it's currently only done with OP-T.
When we started to talk about this, I think it was last Connect, and then we had some discussions with guys coming from a couple of different companies. So we have had a mailing list where we started the discussion, and there were guys from Linaro, ST, Trustonic, Huawei, and a couple of different people. So, I mean, they probably haven't tested this, but they have been at least been with us in the discussion from the beginning. So.
I guess I'd be interested. I mean, even some of the something like Trusty or something where the code is available that you could test against, just to give you some validity to having a generic TE driver, and then if you have interactions with Trustonics and other companies like that. I guess it would help moving towards a common and generic TE drive, which your goal is.
So, Any other questions? Well, thank you.